everyone. I am part of the research team of FEM's at San FEM is a laboratory of optimization in mechanical engineering. So this presentation is part of my PhD project with the main axis is the optimization, but is supported by material tested and FEM analysis. I will show you all the data I have to a PBT polymer with a semi-crystalline polymer. We carry on a traction test where we use a small shape of specimen with 2 notches with effective area between 6 and 8 square millimeters. We shape it from a square part designed to regarding the anisotropic properties on material polymers. So we shape our specimen in the direction of the flow and transversal of the direction to the flow regarding the difference in the properties. Here we have a video which shows us the fracture. We can see the fracture is like a brittle fracture. And regarding the results, for all the specimens, we can see the fracture is in the effective area. And if we put together both of parts, we can see 2 regimes of fracture. At the left, we can see a slow regime of fracture, and the right we can see a fast regime of the fracture. For our purpose, we can say in this one we have a good quality surface of the fracture, and the right we have a bad quality surface on the fracture. Regarding the difference of our test and the test of the curve on stress and strain provided by the supplier, we can see the main difference between both of the curve are the geometry in the specimens, especially because we move our part in quite of the similar condition than the supplier suggests. And regarding the anisotropic behavior of the specimen, we don't find a lot of difference between both the directions. So we can say that on this condition, we have isotropic material. For a FEM simulation, I use the explicit analysis. Why explicit analysis and not another kind of analysis like FEM or something like more developed for this reason? Is because explicit analysis give us a good time to all the simulation. To fit our model, first we fit the force and the displacement on the specimen, and then we fit the quality surface at the surface. When we are happy with our results, we can change the geometry. So in this case, we change the geometry with 1 pre-crate formation and 2 pre-crate formation. We can see on the left the fracture have a linear propagation, but on the right we have a curve propagation. Regarding the next step with the optimization, we are going to study the distribution, the stress distribution just before the crack propagation. We can see in both cases with different geometry. And we also carry out some analysis changing the boundary condition. On the left, we have positive pressure, and on the right, we have a negative pressure in one of the edge of the specimen. We can see in both cases we have different kind of quality surface. But more interesting to the optimization will be the homogeneous shape in the positive distribution of the pressure. We have a homogeneous distribution of stress is quite homogeneous, especially here in the edges. But when we change the boundary condition to the negative condition, we can see near the edges the stress go down. So that suggests that crackinization is more in the inside of the material than the edge of the specimen. For conclusion, we can say we can affect the quality surface with the geometry, the fracture zone, and the initial state of the material and this region. For optimization option and explicit FEM analysis is possible, really.